Hello guys, good day, this is Kuya Chong, and today we are going to talk about something really interesting. Before that, let us hit that intro. So our discussion for today will focus on fluids. It will include forces in fluids, pressure, and of course, viscosity.
Fluids are substances that has the ability to flow. This includes liquids, gases, and plasma.
Let us talk about forces or forces in fluids. There are a lot of forces that act in fluids, but we are going to focus on buoyancy or the force of buoyancy, and of course, we are going to support that with the Archimedes principle.
Buoyancy is an upward force that is exerted by any fluid. This is the reason why heavy objects become slightly lighter underwater, or why is it a little hard to bring an empty bottle underwater. Now, how strong is buoyancy? According to Archimedes' principle, the magnitude of buoyancy is equal to the weight of the displaced fluid. Focus on the displaced fluid. When we say displaced fluid, this refers to how high the water rises up when we are in a closed container. For example, let me draw a beaker. So just imagine this is a beaker. Now the beaker is filled with water. Okay. Let's say the water is 3 milliliters. The volume of the water is 3 milliliters. Now, we added a stone. Okay. When we put the stone into the beaker with water, the level of the water level, rises up to here. Okay. Now, that water is, let's say, the readings of this, the rising of the water is, let's say, 5 milliliters. So, 2 milliliters was added to the volume of the water, right? Now, 2 milliliters is the displaced fluid. So, if we are going to measure the weight of this displaced water, we can get the magnitude of the buoyant force. Now, in getting the weight, remember that that weight is equal to the buoyant force. This weight refers to the weight of the displaced fluid. So the weight of the displaced fluid is equal to the buoyant force. Remember that weight is equal to mass times gravitational acceleration, right? Which is 9.8 meters per second. That is why we are going to use the formula of density. How come that the formula of density is included in here or is mentioned? Okay, first let's erase all things. So again, once again, let's have the weight of displaced fluid. Let's use WD. Weight of the displaced fluid is equal to the buoyant force, which is FB. Now, remember once again that weight is equal to mass times the gravitational acceleration, which is 9.8 meters per second squared. Then I mentioned that we're going to use the formula for density, which is Greek letter rho is equal to mass divided by volume. Okay. Remember that there is mass here and there is mass here. So if we're going to look for the mass, we have to derive this formula into mass is equal to density times volume, right? And that way we are going to get the mass of the displaced fluid. If we are going to get the mass and multiply it with gravitational acceleration, we will be able to get the weight of the displaced fluid, and we will be able to derive the buoyant force or the magnitude of the buoyant force, right? Okay, let's put it into an example so that we will be able to somehow more understand this. Okay, let us say we have here a beaker once again, a beaker with water. So let's have a water here. This is the water level. Let's say the water level is 10 cubic centimeters. Okay, now we added a stone. Okay, the stone, we added the stone here. Let's change its color. And because we added a stone, of course, the water level rises. So the water level rises or increased up to, let's say, okay, here, almost, the beaker was almost filled with water or full with water. So the water level rise up to 15 cubic centimeters. This means that the displaced fluid is 5, right? 5 cubic centimeters. Now, we are going to look for the weight of that 5 cubic centimeters of water in order to get or to know the magnitude of the buoyant force acting on this stone that we just placed. Okay, so we're going to use the derived formula of density, which is mass. Let's change color perhaps. Let's say mass is equal to density times volume, right? So the density of water is approximately 1 grams per cubic centimeters. Then we're going to multiply that with the volume, which is 5 cubic centimeters, right? Sorry. So we're going to cancel out cubic centimeters, but I can place the cubic centimeters. So let's say the mass is 5 grams. So the mass of the displaced fluid is 5 grams. And as I have said earlier, in order to get the weight, we have to multiply mass with gravitational acceleration. So mass is 5 grams times acceleration, which is 9.8 meters per second. 9.8 meters per second squared. So, wait, let me get my calculator. So this is 5 grams times 9.8 meters per second. It is 49. So 49 grams per meters per second, sorry. Again, this is 49 grams per meters per second squared, or 49 Newton. Because the unit for force is Newton, and weight of the displaced fluid is equal to the force of buoyancy, right? So if we're going to make a general formula for this, we can make this, or we can find the buoyant force by multiplying the density of the fluid, the volume of the displaced fluid, and the gravitational acceleration.
Next, we are going to talk about pressure. That would include Pascal's and Bernoullis principles.
First, let us define what is pressure. Pressure is perpendicular force acting on the surface of an object per unit area. So let us take note the factors affecting pressure here. We have the force and area. Okay, so take note that the formula in finding pressure is P, or pressure, is equal to force, divided by area. Okay, Remember that the formula the unit for force is Newton. While in area, we have meters per second squared, which means that in pressure, the SI unit for pressure is Newton per meter squared, or we can have it as Pascal. Okay? Okay. Now, let us erase those things and let us rewrite again the formula. We have pressure is equal to force divided by area. Okay. Now, if we are going to increase the area, what do you think will happen to the pressure? Of course, the pressure will decrease. Right? For example, let's have the force is 3, let's say 3, and the area is 5, so it's gonna be 0.6. If we're going to increase it by 6, the area, the pressure will be 0.5, right? So there is a decrease in pressure if we are going to increase the area, right? What if we are going to increase the force? Of course, if we are going to increase the force, the pressure will also increase, right? So for example, let's have 10, our force is 10 newtons, for example, and our area is 2, so it's gonna be 5. If we are going to make our force 20, then our area will be remained constant, which is 2. Of course, our pressure will be 10. So as we increase the force, having our area in constant, the pressure will increase. If we are going to increase the area, having the force in constant, our pressure will decrease. Okay, now let's go to Pascal's principle. According to Pascal's principle, pressure applied in one point of liquid transmits equally in all directions. So here we have a closed container, or a container containing water and having piston above it. Okay? Now, remember that water is incompressible, meaning we cannot diminish its size, its volume, by just applying force or pressure. Okay? We learned earlier that pressure is equal to force divided by the area where the surface, or where the force is applied. If we are going to increase the force, the pressure will also increase, right? Now, going back here in our illustration, let us first divide this into 2. In the top level of the liquid, we have seen that the piston is touching its surface, right? So meaning there is pressure above it, because perhaps the weight of the piston is causing the pressure. And so, in the bottom division, there is also pressure in there. Now, if we are going to apply force in the piston, we're going to increase the force here in the piston. What do you think will happen to the pressure in this part and in this part? Of course, they will also increase, because according here, if the force is increased, the pressure will also increase. Now, based on Pascal's principle, if the pressure is increased in the top level, the pressure in the lower level will also increase. Now, let's have Bernoullis principle and see how it is related with pressure. So, according to Bernoullis principle, as the speed of moving fluid increases, the pressure within the fluid decreases. Okay, so remember that the speed of a moving fluid is increasing, the pressure decreases. So this means that according to Bernoullis principle, pressure or speed is inversely proportional to pressure. So they are indirectly related to one another. Okay, so let us have a real life example to illustrate this relationship. Okay, so we have here a problem. Water flows through a horizontal pipe with a cross-sectional area of 4 meters squared at the speed of 5 meters per second with a pressure of 300,000 pascals at point A. And at point B, the cross-sectional area is 2 meters squared. So the first thing that we have to find is the speed of water at point B, and the second thing is to calculate the pressure at point B. Now, let us first draw the horizontal pipe. So since it is a horizontal pipe, it will look like this. So horizontal pipe, right? Then it is point A. Let's put point A. Okay. Now, okay. There is also a cross-sectional area at 2 meters squared, which means that the area of the pipe is decreasing from 4 meters squared. Diba, the area of point A or 1 is 4 meters squared. So, sorry, wait. 4 meters squared. Oh my god. That too. Now, the area at point B is 2 meters squared, which means that the area, the pipe is decreasing in shape. Sorry. Okay, it's very difficult to draw it using the pen. Okay, just imagine this is connected here. Okay. Assume this is point B. Okay, this is point B. Now, again, in point B, the area is 2 meters squared. So let us have this as A2. The area 2 is 2 meters squared. Okay, now remember that the water is flowing from here up to here, right? Now, the speed of the water flowing from point A to point B is already said. It is 5 meters per second. Okay, 5 meters per second. Sorry for the background noise. 5 meters per second. Now, in the first thing that we have to look for is the speed in point B, the speed of the fluid in point B. Remember that there is a change in speed of fluid because the area of the pipe is decreasing, right? From bigger area to smaller area. So we cannot expect that the area, or I mean the speed of the fluid is still constant because the area of the pipe is decreasing. Okay? So we are going to cite the continuity equation, continuity equation for incompressible fluids. Oh my god. So remember that if the area increases, the speed increases. Okay? So there is an indirect relationship between the area and the speed of the fluid. While if this area increases, of course, the speed decreases because as what I have said earlier, there is an indirect relationship between them. So first, we are going to look for the speed of the fluid here in point B, because it is not yet given. We are only given the speed in point A. Okay, so to calculate that, as what I have said earlier, now we're going to use the continuity equation for incompressible fluids. So wait, let's change the color. It is speed 1 times area 1. Sorry, wait. Area 1 times speed 1 is equal to the A2 times V2. So we are already given with A1, which is 4 meters, right? 4. Then our V1 is 5 meters per second. That is the speed in point A times 5 is equal to A2. It is 2 meters. While we are looking for the V2. So this is gonna be 20 divided by 2, right? So 20 divided by 2, that is, wait, let's complete here. 20 divided by 2, that is 10. So our speed in point B is 10 meters per second. So this is in accordance to what we have what I have said earlier, that as the area increases, the speed decreases, and as the area decreases, the speed increases. Okay, now we already have answered the first question, which is to find the speed at point B. Now the second question is to calculate the pressure at point B. We first solved the speed at point B because this is, or the data here, the data in point, the data which is the speed in point B is needed in order for us to solve for the pressure in point B. Since we already have the pressure in point A, which is 300,000 pascals, we're going to look at the pressure in point B. Okay, so let us first erase some or a few things here. Wait. Okay, so in finding the pressure here in point B, we are going to use Bernoullis equation. Okay, so Bernoullis equation is like this. Okay, perhaps let's change the color for better visual representation. Okay, so Bernoullis equation is P1, which is pressure in point A, plus rho GH, sorry, rho G, oh my, rho GH plus 1/2 rho V1 squared is equal to the pressure 2, which is the pressure in point B, which is the factor that we're looking for, plus another rho GH2, because here is rho GH1, by the way, plus another 1/2 rho V2 squared. Okay, so remember that here in this part we have PGH1 and we have PGH2. This part here is actually needed whenever our pipe is changing its height. Okay, but our pipe here is not changing its height. It is horizontal and it is not changing its height. It does not shapes like this or like this or whatever, it is a horizontal pipe. The only thing is that there is change in its area. Okay, so since it is horizontal, it is since there is no change in its height, that is not needed already in the equation. Okay, in this problem. So we have P1, which is 300,000 pascals, right? So we're gonna substitute with it 3,000 pascals plus 1/2 density, that is rho. Density of water is 1,000 times the velocity in, or I mean the speed in point A is 4 squared, right? Sorry. 4 squared is equal to P2, which is what we are looking for, plus 1/2 the density of water, which is 1,000 again. Wait, let me move this. 1,000 times the velocity in point 2, which is 10 meters per second. So 10 squared. Okay. So if we're going to multiply 1/2 of 1,000 times 4 squared, that is, oh sorry, sorry, this is not 4, this is not 4 here, sorry for the mistake. Okay, let's erase this one. It's not 4 because we are actually having, the formula is actually talking about the speed, which is 5, right? It's not 4 meters squared, it's 5 meters per second. Sorry for the mistake. So I'm gonna change this into 5 squared. Okay, sorry. Now if we're going to get 1/2 of 1,000 times 5 squared, that is actually 12,500. So this is gonna be 300,000 times, or I mean plus 12,500. So if we're going to add 300,000 with 12,500, that is actually 312,500. 12,500. Okay. Is equal, so that's in the left side. In the right side, we're gonna get P2 plus 1/2 of 1,000 times 10 squared, that is actually 50,000. Okay, that is plus 50,000. 50,000. So if we're going to throw this 50,000 here, it's gonna be 312,500 minus 50,000, right? So if we're going to multiply them, it's gonna be 262,500. So our final answer would be, wait, the final answer would be, let's erase a few things for more space. The final answer would be 262,500. Okay, this would be the pressure in point B here. Okay, now let's go back to Bernoullis equation. According to Bernoullis equation, that as the speed increases, the pressure decreases, which is true enough in our example. In point B, the speed is 5 meters per second. In point B, there is an increase, additional 5 meters per second. That's why in point B, the speed becomes 10 meters per second. So there is an increase in speed. the pressure in point B is 300,000 pascals. I mean, in point A, the pressure in point A is 300,000 pascals. Now, we found out that the pressure in point B is 262,500. So, the principle of Bernoulli is true enough because there is already an apparent decrease in pressure. Okay? So that is Bernoulli's principle.
And finally, let us have viscosity.
What is viscosity? Viscosity is the resistance of a fluid to flow. So this is generally caused by molecules experiencing friction that is caused by their molecular interaction. So fluids with high viscosity will also have high cohesive forces. Okay, for example, we have honey. Honey has a very high viscosity. That's why it is somehow, sticky. It is because also they have high cohesive forces. And they also have high viscosity. Remember, viscosity, high cohesive forces, and high viscosity. This leads to low flow rate. So sa Bisaya pa, hinay ang ijang paglanay. Okay? So this means that if there is low cohesive forces, if there is low viscosity, there would be high flow rate. For example, is water. So water is not so sticky unlike honey or maple syrup. Water or vinegar or even alcohols, they have low viscosity. Right? They have low viscosity. That's why oh my god, what happened? Viscosity. They also have low cohesive forces. This is the reason why they have high flow rate. They flow very fast.